with TensorFlow. One of the things that I do want to call out is we have some really good courses in machine learning and AI and neural networks, etc. This is not meant to be a replacement for that. This is meant to be an introduction to an open source tool that you can use to do AI and machine learning, etc. So I'm not going to get into the intricacies of AI. We have professors who make that their entire career. So this is going to be maybe at a higher level. For some of you who have already taken those courses, maybe it'll be at a higher level than that. But it is a good start, and I think it'll get you kind of excited about what's actually available out there. We have a couple of these types of modules. Can I make this any bigger? There we go. This one and the last lecture we gave, MongoDB, were actually adapted from presentations that previous students have given, either in our course or in this course. So this material was adapted from some material that Olivier Poulin put together back in 2019, I think. It's progressed from there, but I think it's still pretty good. Unfortunately, he did it on TensorFlow 1, so it has had to change to keep up with the times as we've gone along. Shoot. If you go to the TensorFlow guide, you can ignore this, read high-level APIs and read low-level APIs. What I want you to read are the TensorFlow Basics. Okay, if you just kind of read through the TensorFlow Basics and yeah, read through the TensorFlow Basics and you know, read what eager execution, read about tensors, read about variables, and I don't think this is too long. Just read the entire TensorFlow Basics section and read the Keras section. Okay, I apologize. I'll change those slides. I was planning on coming back to that, and apparently I didn't actually do it. But these are the sections that we'll be taking questions from for the test, and these are the sections that will help you out as you progress forward. So it'll be TensorFlow Basics and Keras. Yeah. In fact, I think, well, let's just leave it at that before I cut off too much and then we aren't ready. I'll post a note on that. I do apologize. I wanted to read. This entire guide has changed, and the high-level APIs and low-level APIs no longer exist. So there is no way for me to have you read that, and I had intended to change this part after I'd gone through the entire lecture, and I forgot to come back to that. All right, so introduction. So what is TensorFlow? TensorFlow is an end-to-end open source platform for machine learning. It lets researchers push the state-of-the-art in machine learning, and developers easily build and deploy machine learning-powered applications. And this is directly from the TensorFlow or website. We like to refer to definitions that people give themselves whenever possible because, well, that's kind of the world that they're living in. So, you know, basically, TensorFlow allows us to develop machine learning applications faster, and allows us to do research in both machine learning and machine learning applications. And the cool thing is that it is open source. So, open source, this is something that doesn't really come out from that first little blank, but in order to do machine learning, you need the ability to do high performance numerical computation. So actually, what we're going to do in lecture today, in lab, you'll actually do a machine learning neural net kind of application. We're not going to do that today in this class. We'll set you up for it. But what we're going to do is we're going to do things actually in this high performance numerical computation world instead. We'll use a little bit of learning and training, differentiation, curve following, but it's not going to be recognize this dog from this cat kind of thing just yet. Because it's high performance, it deploys on CPUs, GPUs, TPUs. In other words, they are pursuing cutting edge type of applications. It is largely tensors, which are essentially two-dimensional arrays. So numerics are a big part of what they do. There's a lot of training involved in actually determining what parameters best fit your model, and that training requires that extensive gradients and double derivatives be calculated. So it does actually support things that allow you to do parallel and distributed processing on cutting edge processors. You can run it on desktops, clusters, mobiles, edge devices, lots of places you can deploy it. And it was originally developed by Google Brain Team within Google's AI organization. And like so much Google, they actually made it open source. Of course, at the same time, they also have the Killed by Google website with all the things that they made open source or put out there into the world and then, killed. I'm looking for Google. Yeah, Google Fiber TV was killed. Lots of stuff been killed by Google. Hopefully TensorFlow will not join them. But you always have the option, since it's open source, of continuing on from wherever they decide to leave it. TensorFlow is a numerical computation library, but it also has strong support for machine learning. What you'll find out is that along with being able to operate on tensors and do a lot of intensive mathematical computations, it also allows you to build things like neural nets and transition between them and do pre-processing, etc. And it has strong support for deep learning, and it has a flexible numerical computation core. Again, all of these things, if you actually want to do AI computations, you need the ability to do mathematics, and TensorFlow supports them. Okay, I didn't update this list. It seemed kind of unnecessary, but a lot of places use TensorFlow. Coca-Cola, your Coke is generated on a TensorFlow machine with a CPU, a Coke processing unit. Boom, boom. And it goes on for a couple of pages. Again, I didn't update this, so this was the state of the art in 2019. It seemed big enough to be impressive without needing to be extended, and I expect that although some of these may have gone away, a lot of them still exist. By the numbers, TensorFlow is widely used. So if you look here, this is from I believe this is from 2019. Okay, but the link still works. You can go out to TensorFlow, and if you go out to TensorFlow, you can find the TensorFlow repository. All this stuff is still current. Let's just do a little comparison. In 2019, when I generated this slide, there were 52 repositories, 160 people. And how many commits? There were 53,075 commits. In 2 years, that's doubled. It's now about 108,174. There used to be 27. I think those are active branches. There are now 41 active branches. There used to be 1,932 contributors. Now, 2 years later, year and a half later, it's 2,948, 134 releases now. This is the fun one. There were 221 open issues back in 2019. Now there are 3,836, but there are also 27,000 closed. So it looks like the TensorFlow backlog is almost 4,000 issues. And during that time, I should have went back and seen how many were closed in 2019. But they're going through issues really fast, and yet they're still building up an increasing backlog. And they claim it's open source. It is actually licensed under Apache 2.0, which is, a pretty good license for us, in that the only thing that it really requires you to do is to maintain the license, to post the license and the copyright notice and state changes. You can use it, you can modify it, you can distribute it, you can use any patented code that somebody contributes to this library. They give up the ability to assert patents against users of TensorFlow, and you can use it for private as well. The only thing, Apache is one of the good ones. It's relatively permissive. The only thing it doesn't allow is trademark use, liability, or warranty. In other words, you can't take the TensorFlow or Google trademarks and use those, but you can use you can use the library, but you can't say it's from Google. So here's a nice one from a good note from, looks like Hunter still. As I found, as projects get bigger, more and more issues are duplicates or low effort / knowledge issues from end users not familiar with how things work. That is exactly the case. What we're wondering, one of the things, and he says he'd be curious as to the percentage of real issues, and that's a really valid point. And that's why it's always possible to go into a new, if you wanted to become a TensorFlow, part of the TensorFlow main, and assuming that TensorFlow main includes contributors outside of Google, you could go into these issues and start triaging them. And you could take on some really easy issues, low effort, low knowledge issues from end users not familiar with how things work, right? And either close them as inappropriate or propose that they be closed as not inappropriate, kind of do some tending to the garden, as it were, or actually solve them. And by doing that, you would get the experience in working with TensorFlow, but you'd also tend to make yourself more a member of the community. So if you want to get into a community, as projects get big, these things do tend to accrue. And it's good and bad, right? It's hard to separate out the really interesting and real issues from issues that have just been put in by low information, low effort users, as Hunter says. But it does actually give you the opportunity to go in, and as you learn the system, at some levels you have to know the system in order to triage. But it does give this place where newcomers can come in and actually start working with the code and try to build upon what's been done. Anyway, I thought that was kind of cool. Especially what I like to see was how these numbers have grown. They have doubled their number of commits, almost doubled their branches. Now, if they're doing if they're deleting branches as they go, and they're running one branch per major issue, they're working on. You can see they've almost doubled their number of branches, but they've also almost doubled their number of contributors. One of the hardest things about an open source project, and it's one of the things that Google actually does right, even if they do kill a lot of stuff as they go forward, is when they start up a project, they have the ability to really start up a project. So TensorFlow does have an extensive community. We can come in and look at TensorFlow. And you know what? I'm going to do this the old-fashioned way. We will open this in a separate window so that I don't have to keep paging back. Right? They have this extensive network, and they have a number of ways. Right on this front page, on the community page, right? It tells you how to get involved. It tells you how to contribute. Right? Community values. This is how you're expected to behave. This is how you can do your first commit, right? Here's where I stole the TensorFlow was originally developed by research and engineers, right? Very nice and very easy to find, very welcoming page for how to get people to contribute. There's discussion groups, right? So they have multiple discussion forums if you want to start interacting with them. These look like they're geographically distributed. And you know, this page is just all sorts of, you know, requests for comments. Requests for comments are where there can be proposed, they publish proposed changes or features, and you can go in and comment on them and help them develop it the correct way, right? You're kind of the user testing environment. So there are a lot of different ways that Google, you know, sets up this sense of community. If you have something this extensive, you know, don't put this, you know, don't give me something like this in your presentation. You'll have to condense it, because to talk about everything that Google provides would use up all of your final presentation time and never get past community organization. But this, when we're talking about community organization, this is the kind of thing we want to look at, right? They have, you know, extensive community pages, contribution guidelines, you know, help, technical questions, bug and features. They have, you know, mailing lists for, you know, bugs or for keeping up, right? So they basically have pretty much any way you want to interact with Google, you can actually do it, right? And here you can see the mailing list for TensorFlow announcements, mainly announcing that new versions have come out. Finally, what was the one that I wanted to? Oh, they have a blog, security advisories. They have a YouTube channel. I'll throw you somewhere in this presentation. We'll throw you into their YouTube channel. Anyway, lots of stuff going on, lots of ways to interact. And here's another way that they actually interact, right? They have conferences like Google I/O on May 18th through 20th that you can actually register for and attend. So on top of all these other online ways of attending, and I'm not sure whether this may actually be online this semester as well, but or this year as well. But so on top of everything else, they also have conferences where you can go out and interact as well. And it's back online. Free for everyone. Register now. Go ahead, right? It's free for everyone. Register now. And I think it's online, so you don't have to buy a plane ticket or anything. All right. They also participate in Stack Overflow. You know, there's pretty much you can get answers on TensorFlow pretty much anywhere. TensorFlow is available on GitHub, so we can actually go out and go to the GitHub page, right? And we can actually do an analysis. And these are all the commits since, sometime in 2015 out through, you know, today. You can see old TensorFlow Gardener. I think that may be the automatic push guy. But he has 7 million, yeah. Right, 7 million lines contributed, 7 million plus lines contributed, and 5 million lines removed. Yeah, I think it is actually a bot. I think it's the I think after you get your, I would have to verify it, but I expect that it's a bot that gets credit for all of the merges and everything. But you can see there are a lot of contributors as well. I think we've decided there were 2,900 We're not going to see nearly that many, but it's an active community. There are no lulls in the overall graph. You can see that this person came in sometime in 2018 and continues to today, whereas VRV pretty much was there at the start, but has kind of petered out over time and doesn't commit nearly as many things. So you can see different people being active in different parts. Cheshire didn't start until 2019, but at this point they have almost 570 commits into TensorFlow. So, if you want, right, Benoit Steiner, he was the major, the number 2 contributor back in 2019. Now he's the number 8 contributor. And you can see he has made no contributions since part of the way through 2018. The point is that this is an active community. It's an active community with people starting and stopping. So if you do want to get involved with the community, there is evidence that that's available to you. They do take new people in. They do roll old people out as they reach end of life, just like your car. Every now and then you got to get rid of your old car. Well, you got to get rid of your old contributors. No, you can see some people somewhere up here come in, die down, come in again. So anyway, I just kind of liked that graph. I thought that was pretty interesting. And by the way, they have an active blog. I think I was on the other page, but the reason I have this in there is the blog page changed. And you can see that, the latest blog post was April 1st. There was one on May 3rd. There's one on May 2nd. I'm sorry, March 3rd and March 2nd and March 1st. So, there's an active blog where you can go, just like YouTube, get your fix of technical fun. All right. Anyway, I've kind of find this, I kind of love this organization that Google has. This is what you can do when you have way too much money and a lot of time and you want to build an open source project, right? This is, they have everything. Whew. How many more of these do I have? A couple more, not too many. Okay, so they have an issue tracker. We can go into the issue tracker. Right, I think that we had still 3,860 open, 27,254 closed issues. And, you can kind of go in here and look at them. This is a feature label. Somebody's actively culling these as we go along. This was submitted and then labeled and assigned, all just about a few hours ago. And again, as always, if you want a complicated solution that you won't understand until 2 years after you've used it, you can always go to Stack Overflow as well. I'm a big proponent of Stack Overflow when you're actually trying to accomplish something commercially, or when you're trying to just resolve a problem. I'm not really in favor of Stack Overflow as a teaching tool. It gives you, the answers are too short and the insight is sometimes suspect, but you can find quick answers to things that you actually need to find answers to. So when you're using your tools, pick the tools based on what you're actually trying to accomplish. Stack Overflow is good for, I have this nagging problem that I'm trying to get through. I need an answer. It's not good for, I need to understand what's going on. Not nearly as much. Okay, and there are others. I mean, they have a Twitter, they have YouTube, they have release notes, it goes on and on and on. Like I said, Google employs a lot of people. They employ a lot of technical people. They also employ a lot of people who are not necessarily as technical to do things like do communications for them and help them to generate communities of this kind of scale. So for as long as Google's been out, I mean, they like to, when they do kill a lot of things, but when they enter a new area, they like to do it in this big way. And TensorFlow is still relatively new. I mean, I think we saw the contribution started in 2015. So it's, less than, about 6 years old. Okay. Okay. There are a lot of ways to run TensorFlow. You can use a virtual environment. You can use native pip. You can use Docker. You can use source. You can, when I say use source, you can actually download and build TensorFlow from the GitHub source. Like, it's open source, right? That's the whole purpose. Normally, I would recommend using Docker, and I think all of these slides are generated using Docker. I think I went through the entirety of this lab using Docker. If we need to, we'll go back to that. I'm going to try using just the WSL install. For what we're going to do today, it worked more smoothly and seemed like, and going to another Docker container seemed like overkill for what we actually want to show. So hopefully I'm remembering how I did this correctly, and we will go on. If you do want to run it in Docker, that should do it for you. I mean, it works for me. I did start getting issues with having too many things running while trying to tape. So again, like I said, I'm going to try to do this just on WSL on my installation. But Docker will run. It will pull it down. It'll pull down a full environment for you with bindings to Python, mapping port 8088 on the container to point 8888 outside the container. And you can run Jupyter Notebooks, and it starts up an interactive session. So at this point, you're at a prompt. After you've done this, you're at a prompt in the TensorFlow Docker, and you can actually start running. You guys have all seen Docker run, so I don't think I'm going to do that for right now. We'll try moving on from here. Once you've done that, you're going to need to validate it just to make sure things work. And in fact, we'll have to download some more stuff than that. Let me pop my handy dandy notebook up and let me start. Let's see. Okay, so here's my handy dandy notebook. You can see that I just saved a bunch of my changes that I still have to go back and change a few more to remove a few typos. But we can come in here and Docker uses Python. Is this going to work for you guys? Can you guys see this? I think I need to run Python 3 though. Let me get back to where you guys are. Any questions? And that looks, yeah, that's legible. Okay, so you can come into Python 3. You can do something like import TensorFlow as TF, and when you have something like TensorFlow is a lot of characters. Your Python lines will start getting longer and longer and longer. So importing it as TF allows you to have the same benefits of namespaces while limiting how much you actually have to type. This is just a sanity check to make sure that you have TensorFlow installed correctly. Once you do, TensorFlow, as the name kind of implies, does most of the things based on tensors. So we can define tensor constants, right? Constants are things that are not expected to change. So we can define A as the TensorFlow constant 3. By the way, these errors that are coming up, these are errors because I don't have a GPU configured. And I don't think I have a GPU at all on this laptop, but I certainly don't have one configured. These will start going away now that we've kind of hit most of the other issues. We can set up another constant B right? So now we have two constants. We can look at them. So A is a tensor. It has no shape, right? Because it's just a scalar. But it's of data type at 32, and it has the value in NumPy of 3. And we can do the same thing for B. Why I pulled up A to change it to B? Who knows? That has the value 5, and we can do something like C equals A plus B, and these are really intense numerical computations. But the point is just to show you that at its core, TensorFlow is just a numerical library, right? So we can assign things to variables. We can do mathematical operations on them, and the mathematical operations can be assigned to variables, and we can actually compute some mathematics here. So if we add A and B together, we can come up with a variable C. And if you're familiar with NumPy, what you'll find out is that underneath the covers, TensorFlow makes pretty good use of NumPy, and in fact, there are a lot of cross-pollination kinds of things. So in NumPy, so if we want to come in here, we can say import. I think I have NumPy installed. Yeah, right. We can set up an array of zeros. A equals np dot zeros, and I'm going to say 2, 3 because otherwise you can't actually tell. Right. That gives us 2 rows and 3 columns, or we can do ATF equals TF dot zeros. 2, 3, and that gives us, well, there you go, the same thing, right? A 2 by 3, 2 rows, 3 columns array of all zeros, and you'll be surprised to hear that this actually works with ones as well. Right, and we can do the same thing with BTF, right? So NumPy and TensorFlow have a lot of similarities, and you can do things like do reduces, like if we want to axis 1. I think this will reduce it to sum up the rows. Right, so this sums across the rows. 1 plus 1 plus 1 equals 3. 1 plus 1 plus 1 equals 3. And we can do the same thing with TensorFlow, except now it's called a reduce sum operation. And the notation is just slightly different. Okay, but it does the same exact operation. And what you'll find is that all of these work. You can do a.shape. Oops, you know what? I did a TF reduce on an NPy array. Doesn't matter. Still gives us the same. And you can do a get shape, right? A.shape or ATF.getShape tells you how your tensor is organized, right? By 2 by 3 matrix. You can change it. think I need to make this a 1-6. Right? So we've turned it from a 2x3 matrix, two rows, 3 columns, into a 1x6 matrix. Right? So you can do all of this with your matrices. Kind of pull them together. Reshape may come in handy when you're looking at curating your data in the lab. And you can do things like BTF times 5 plus 1. Right? That'll take the B tensor, multiply every entry by 5, and then add 1 to every entry. And we can do okay. MapMul doesn't do MapMul does a dot product, not a matrix multiply. Anyway, good enough. And then of course you can reference any of the entries. Right, or any of the rows or any of the columns. Okay, so all of these are, just, that was a little bit of a long-winded exploration. You guys can read that just as well as I could type through it. But the idea is that, again, this is just a mathematical library, right? You can do mathematical operations and get answers out, just like any other mathematical operation library. TensorFlow does a lot to make this run on your GPUs. It does a lot to make it fast, but it also allows you to do things like calculate gradients, more complex calculations like calculating gradients and throwing together neural networks that other libraries just can't ask you to do. The base usage in version 1, important safety note here. Maybe I should go back to this slide. So in version 1, TensorFlow was built for engineers, people who were actually doing research and who wanted to be able to analyze the computation graphs so that they could improve the performance. Because of that, the execution graph was made explicit in TensorFlow 1.0. The first part in TensorFlow was building a graph. You would build a graph that would subsequently, with all the operations you wanted to do. And then once you'd constructed it, you would execute it. And then you could execute the graph over and over again in an iterative fashion if you wanted to do something like do learning to generate the weights of the nodes of your neural network. But what they found out was that most people weren't really interested in doing research on optimizing TensorFlow. They just wanted to use TensorFlow. So these things that allowed the engineers to go in and tune TensorFlow and make it effective, experiment with parallelism, etc., turned out to be confusing to people who were actually just trying to use TensorFlow. So they got away from this idea of building this execution graph and then executing it in TensorFlow 2 when they migrated to TensorFlow 2. Now the graph still exists, so those people doing that research can still improve it. You can expect that as new GPUs come out and as new progress is made on algorithms, that they will continue to follow that. But for the time being, at least, they've kind of hidden this graph again behind behind a more traditional interface, and you can still get at it, but you are free to ignore it, and ignore it we will. All right, so that's kind of like the 30 seconds, 45 minutes on TensorFlow. Let's get into a little bit more about deep learning. And again, I'm not going to conflict with anything that you've learned from Professor Malik or any of the other professors, Professor Mushtaq, whoever else teaches deep learning and machine learning. That's not my field. I don't feel comfortable presenting myself as an expert. But deep learning is a machine learning method. It's a little bit more, it's more complex, but has broader applications than classic task-specific algorithms. So instead of having to encode an algorithm that performs a task, what deep learning allows us to do is it allows us to simulate or to build up a network of interconnections to take some input and transform it into some output. And then within that network of connections, we can just, given sufficient training data, we can just optimize the network by doing a gradient following until the network, when presented with the input, will give us the output that we want with high probability. So this is all positive things about it. Do I say anything negative about it? The problem with it is that you're doing these complex applications with these complex operations with broader applications, but you don't actually have to find out why the machine is thinking that this input maps to this expected output, right? So one of the things that's hard about machine learning, about deep learning, is that you don't always know what aspects of your model resulted in the answer you got. So when things go wrong, it's harder to debug and it's harder to figure out what's actually going on. So that's kind of a drawback. You have this black box, and as long as everything is going good and you're throwing inputs into it and you're getting outputs out of it, everything's great. But if you have to try to figure out why all of a sudden something stopped working, or what inputs are or predict what inputs are going to break, you can't. Now, in fairness, right? We don't always know in our own visual systems or in our own mental models why we're able to recognize something or when something flips. I don't know if you guys remember the dress image from a few years ago. There was a dress. To me, it looked tan, and to others, it looked dark, deep blue, and it depended upon the light cues that you were picking up in the scene, apparently. Whether you decided that it was a dress being illuminated in shade so that the dark colors were just the effect of the shade being cast onto the dress, or whether it looked like, or whether you took in the visual cues that said it was in light and it was a dark dress being illuminated by a relatively bright light, something like that. I did not go into the neural or the visual stuff on it, but I did notice that when I took it out into brighter light, the effect was more pronounced. Or different than when I was in dimmer light. I was able to get it to flip colors a couple of times on myself, and that was a very weird feeling for that optical illusion. Anyway, neither here nor there. Those types of things are hard to predict with neural nets, but they're hard to predict with our own vision systems as well. So maybe that has to be weighed. So what a neural network is, it's a collection of units or nodes. They're considered to be artificial neurons. That's why they call it a neural network. And what you have is you have layers of these, and you have a flow through them, and you have interconnection patterns. So for example, you'll often have an input layer where you present. This input layer takes, obviously the inputs. So in here we have 3 inputs to our model. They go into these 3 nodes. And then from this input layer, what happens is the values get distributed to all, right? So node, this first node up here, node 0, distributes its values properly weighted, right, to all of the members of the next layer, and then the next one does the same, and so on. And this interconnection pattern is part of what you can set up with TensorFlow. We'll generally use a dense interconnection pattern, which means that everything in one layer is connected to everything on the next layer, right? So you can see that this is a input layer, we have an output layer, and then we have one or more hidden layers. The values from each node are transmitted to everyone in the next layer, modified by this kind of weighting function, and biases. And then what we do is they form an equation that transforms the output from this node into the input of this node. And then what we do is we make a big matrix of these weights and biases, and we train our model so that by presenting it with, looking at the outputs and presenting it with real data, and then we train it until it repeats or can give us back the data that we want, at least with high percentage-wise, give us the answers we're looking for on the output. Once we've trained our model, once we've calculated the appropriate weights and biases that map from our input to our output, well, then we can try it against novel inputs and use it to predict what the values would be on that novel input, if that makes any sense whatsoever. The key is that we have layers. The layers are interconnected. They're interconnected using a specific mathematical formula involving a weight and a bias. And we adjust these weights and biases until we get the results we want on the output layer. And that's a trained neural net. We can use a couple of different models for our neurons. A perceptron is basically a 0-1. So that means that the output means the signals between neurons can only be binary as well. It either is or it isn't, right? So what you're trying to do is you're trying to, if it sums up, if all of the inputs to a node with all the weights sum up enough, then it outputs a 1. Otherwise, it outputs a 0. And that's just, a really simple model. It's this kind of disjoint graph, 0 until it reaches the threshold, and then 1. There are other more advanced ways of doing it. For example, instead of having that simple discontinuous formula for what a neuron fires at, you can have something like this, which is an exponential, and it stays low for a long time, then gradually or more gradually rises, and then stays at high for a long time. It gives us nuanced outputs. This is really useful for something like, let's say, in a lab, you wanted to detect what the probability that an image was a pair of socks versus it was a shirt or a pair of sandals. This would allow you to express things like percentage matches, right? How closely does this output or does this input match what we think a sock looks like, for example. So the difference between the two is just that this uses an exponential function and this uses, essentially a 0-1 function, a binary function. Deep learning, right? Simple neural networks have, one layer. Deep learning can have multiple layers and they can have multiple interconnection patterns. This one shows 3 hidden layers, right? You have your input layer here with 8 inputs. And then we have hidden layers of 9 nodes. And then we have an output layer of 4, either classifiers or information. So for deep layers, for deep learning, we can stretch together multiples of these, and we can actually also use feedback and more complex ways of connecting the different layers. Okay, so I kind of alluded to this a little bit, but what we want to know is how to train, we need to do this training operation on our data, and we want to know how to train. So for each neuron, we have a number of inputs, and we have a predicted output, or we have an output, right, from the neuron. And what we want to know is we want to know how changes in the input affect changes in the output, right? So the partial of L with respect to z is the change we want to see, the direction we want to see z move. And given we want z to move in this direction, we can calculate the partial of the z function, knowing we're using, for example, a perceptron in here. We can calculate how z varies with respect to each of its inputs. And that will tell us how we want to adjust these inputs so that they better match to the answer we want to get. Okay, we're going to use some variant of gradient descent, which is going to calculate the gradient of what direction we want to move these things in, and then change them based on this directional constant. And this can get very complicated as your networks get very big, right? Basically, we get a vector of all the errors. The errors give us how we want the output to change. We use that to backpropagate all of, right? We calculate how we want these output layers to change. We calculate a direction for those to change. That allows us to calculate a direction we want each one of these inputs to change, which then gets propagated back through all of the weights until we reach the input. Right? We don't want to change the inputs. The inputs are going to stay constant.